Hello, this is a video tutorial on the Boyer-Moore-Horspool string matching algorithm. The Boyer-Moore-Horspool string matching algorithm is a simplified version of the Boyer-Moore algorithm, a famous string matching algorithm that is actually quite difficult to implement. Luckily, Horspool came up with a simplification, which I'll explain later, which make this algorithm much more simpler to implement. So why string matching? Well, string matching is a fundamental part of computer science. I've written a few important applications here. The algorithm I'm going to be talking about today is particularly applicable in security. This is because it's efficient on large alphabets. So the naive algorithm for string matching, for searching for a pattern in some text, simply iterates through the text, character by character, and then at each character index, it compares the pattern to the text. You can see that I've written a pseudocode here, and it's quite easy to calculate the efficiency of this algorithm. This loop over the text here is O of n being the text length, and this loop over the pattern length here is O of m being the pattern length. So it's quite simple to see that this naive algorithm is order nm efficiency. I've written up a quick example here to demonstrate the naive algorithm. So we're searching for this pattern here, ABB, in this text right here. So you go ahead and start from the first index, A, B, B. So this A here matches, this B here does not. So then you go ahead onto the next index, A, B, B, mismatch, and so on, comparing your characters left to right along the text until you reach your pattern. And particularly this example has made 13 comparisons between the text and the pattern, and I'm going to demonstrate the same example with the Boyer-Moore-Horspool algorithm. So we're searching for the same pattern in the same text here. One main idea of the Boyer-Moore-Horspool algorithm is to instead compare your pattern right to left in the text. So when we position our pattern here at the first index, we're actually comparing this B here first to the text, which as you can see is a match. And then we go ahead onto the next character to the left, which does not match. In contrast to the naive algorithm, we don't simply move along the pattern by one index, although in this first case we do. We instead try to skip along by a certain amount so that we align this last character, the rightmost character in the text, with the rightmost character in our pattern of that same character. So this B here, we're trying to align this with the rightmost occurrence of a B in our pattern, which is right here. And as you can see, that only moves it along by one. And then again we check right to left. This B here, however, immediately does not match. So we align this A with the rightmost occurrence of an A in our pattern, which is simply the first A since it's the only A. And in this case we skip ahead 2, which is an improvement on the naive algorithm. And then we do the same thing again. We're checking this B against this A, and it's not equal. So we align this A with the rightmost A in our pattern, and we do it here and find our pattern in the text. So how does this actually work? How do we actually decide how far to skip ahead when our pattern does not match in the text? We pre-process the pattern text and we build a table for each character in the alphabet. And for each character in the alphabet we skip a different amount. So when we're at an index, say this first index here, and we know that our pattern does not match because in this example these two characters do not match, we always take this rightmost character in the text and use this to determine how far we skip, because we want to align this character with the rightmost occurrence of that character in our pattern. And this is Horspool's simplification on the Boyer-Moore algorithm, which performs some more complicated tasks to do this. Okay, so what does our table look like in our example? In our example, we only have two characters in the alphabet, the A and B, of course, and we need to fill in values here to say how far to skip ahead to align with these characters in our pattern. So we go ahead and look at our pattern, and we assign values from right to left, ignoring the last character because it's already aligned. And we just fill in the table of characters in our alphabet with these values. In here we would have a 2 for the A and a 1 for the B, and say there was a character that didn't occur in our pattern, say a C, we would just want to set this to our pattern length, which is 3, so that we just skip ahead past the C and ignore it, because we know that our pattern cannot occur with that character. So how efficient is this algorithm compared to the naive implementation? Well, the pre-processing, we have to iterate for every character in the alphabet to initialize their values in the table to the pattern length, and then we have to iterate through our pattern to initialize the values of those characters to their values in our pattern to say how far we have to move to align them. And so this takes time of order the pattern length plus the length of the alphabet. Now the worst case, we're only going to be skipping along one place at a time, and this is the same as the naive algorithm. So in the worst case we get the same efficiency as a naive algorithm, however in practice it's usually much more efficient than this, and in fact in the best case we get order n divided by m, which is a massive improvement. This best case occurs when we skip the entire pattern length each time we mismatch. So I have some examples here to demonstrate this. Here's an example of the worst case occurring. We're finding x, y in a whole bunch of x's and a y. So here our table would look like this. So just to quickly demonstrate, we see that this y here does not match. Now we see how far we skip ahead in our table based on this x, and it's only 1, and we repeat this over and over again, skipping only 1 ahead each time. It's the same as the naive algorithm until we finally reach our match, and you can see that this is the same number of comparisons as the naive algorithm would be. So an example of the best case occurring, finding x, y in this string here, z, 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 x, y. This of course happens because z is not in our pattern, so we simply skip the entire length of our pattern every time we see a z. Anyway, our skip table here would look something like this. So as usual we start here at the beginning of the text, we compare this y to the z, is not a match, so we look up the z here in our skip table, and we skip ahead 2 places to here, and you can see here, and so on and so on, and we reach our match, and in this case we skip our pattern length at each iteration, which is the most efficient possible we can get. So to summarize, in practice this algorithm runs much faster than O m of n, even though this may be the worst case scenario, and it indeed works very fast on larger alphabets. This makes sense when considering that any character in the alphabet that does not exist in our pattern causes us to skip the entire pattern length each time and help us approach the best case scenario. Thank you for watching.